Good afternoon, students. Today we shall start with the design of two-way slabs. In the previous session, we have completed the design of one-way slab. We know how to calculate the depth required for a one-way slab, how to calculate the loads acting on the slab, then check for the deflection, shear, as well as to calculate the reinforcement details. Now, in a similar way, let's go ahead with the design of two-way slab. Hello, am I audible? Is the screen visible to you all? Is the screen visible?
Yes, ma'am.
Okay, let's start with today's session with the design of two-way slab. Here is the numerical. Design a RC slab for a room measuring 6.5 meter by 5 meter. The slab is casted monolithically over the beams with corners held down. The width of supporting beam is 230 mm. The slab carries superimposed load of 4.5 kN per meter square. Use M20 grade concrete and Fe 500 steel. So here is the dimension of the room, which is measuring 6.5 meter by 5 meter. Now it is not given directly whether you are supposed to design it as an one-way slab or two-way slab. So first and foremost, you are supposed to check which type of slab it is. So in order to check the type of slab, what we are going to do, we are going to take the ratio of these two dimensions. The longer span to shorter span dimension, that is Ly by Lx ratio. 6.5 divided by 5. This ratio is less than 2. This ratio of Ly by Lx is less than 2. Hence the slab we can say that the slab is to be designed as one-way slab. Sorry, two-way slab. Since the ratio of Ly by Lx is less than 2. Even if it is equal to 2, we are going to proceed with the design of two-way slab only. Only if Ly by Lx ratio is greater than 2, then we proceed with the design of one-way slab. And here the slab is resting on the beam and the slab is designed as two-way restrained slab. Two-way restrained slab. Why restrained slab? It is two-way slab, we have understood. Why restrained slab? Here is the data. The slab is casted monolithically over the beams with corners held down. With corners held down. So here let me go ahead with the codal provision with corners held down. See here, in table 26 of IS 456, we have different bending moment coefficients for different panels and the ratio of Ly by Lx also. And this table refers when we provide the torsion at the corners. Why do we provide the torsion at the corners? In order to make sure that the corners are not lifted up. So if the corners are held down, then it is confirmed that there is torsion reinforcement at the corner. So here there is one more table 27, but only the difference is here corners are free to lift. The corners are free to lift. They are not held down. So depending upon the clauses given, you are supposed to choose which table has to be referred or which case has to be considered. Now, according to the numerical, the width of the supporting beam is 230 mm. and the slab carries an superimposed load. This superimposed load is nothing but live load of 4.5 kilonewton per meter square. Use M20 grade concrete and Fe 500 steel. And here the slab is casted monolithically over the beams with corners held down. Okay. Then corners are held down. That means torsion reinforcement is to be given. So if torsion reinforcement is to be provided, so obviously we are going to refer table 26. In table 26, which of these 9 cases we need to refer? Which of these 9 cases we need to refer? In order to decide that, again here there is no details like one of the edges discontinuous, two edges discontinuous, two adjacent edges continuous. There is no such data given in the numerical. So they have just said that the slab is casted monolithically over the beams with the corners held down and the width of supporting beam is 230 mm. So it is simply supported on a beam of 230 mm width. So if it is simply supported on a beam of 230 mm width, then we consider the case 9, that is 4 edges discontinuous. We consider the case 9 of table 26, that is 4 edges discontinuous. In this case, see here, we have only the positive moment at the midspan. We have the positive moment at the midspan. If suppose the edges are continuous, then if the edges are continuous, then even we need to consider the negative moment at the support section. Only if there is continuous edge, we are supposed to consider the negative moment at the support condition, supports. So since the 4 edges are discontinuous, we will only have the positive moment at the midspan. And now we need to consider the short span coefficient alpha x and long span coefficient alpha y. So short span coefficient alpha x. So this alpha x value depends upon Ly by Lx ratio. This depends upon Ly by Lx ratio, and for long span coefficient alpha y also it depends on Ly by Lx ratio, but whatever may be the ratio, the long span coefficient does not vary. Okay, with this background, let's start with the design now. Now, first and foremost, as we have to calculate the depth of the slab, so we are going to assume the slab to span to effective depth ratio. Again, from the codal provision, we are going to refer to two-way slab. Let me show you the codal provisions. Yes, here in the note for solid slabs. For two-way slabs of shorter spans up to 3.5 meter with mild steel reinforcement, the span to overall depth ratio given below may generally be assumed to satisfy vertical deflection limits for loading class up to 3 kN per meter square. For simply supported slabs, it is 35. For continuous slabs, it is 40. And if there are high strength deformed bars used in the design or used in the slab, then the values given above should be multiplied by 0.8. The values should be multiplied with 0.8. So here approximately we have considered the span to effective depth ratio as, yes?
PDF visible, ma'am.
PDF is not visible?
Yes, ma'am.
Yes, ma'am.
Is it same with the all? Is PDF visible or
Yes,
no?
ma'am. No, ma'am, not visible.
Yes, ma'am, not visible.
Not visible.
Yes, ma'am.
Now is it visible?
Yes, ma'am.
This one? Is this visible now,
Yes,
codebook?
ma'am. Yes, ma'am.
Okay. So let's continue. Initially, was it visible or should I explain it once again? Hello, should I explain it once again?
Yes, ma'am.
Okay. See here, in the design of RC slab, the room dimension is being given that it is 6.5 meter by 5 meter. Now, in the numerical, it is not clearly been mentioned that whether it is to be designed as one-way slab or two-way slab. So, we need to calculate the Ly by Lx ratio, that is always larger span to shorter span ratio. So, if we consider larger span to shorter span ratio, it comes out to be less than 2. Since it comes out to be less than 2, as per the discussions in the previous session, what we need to conclude that it is to be designed as a two-way slab. Ly by Lx ratio is less than or equal to 2, then we need to design it as two-way slab. And here the slab is resting on the beam and the slab is designed as two-way restrained slab. If we say that it is a restrained slab, then from the codal provision, we need to refer to table 26 of IS 456. Table 26, because here we have the provision for torsion at the corners. Why do we provide the torsion reinforcement at the corners? In order to make sure that the corners are not lifted up. In order to make sure that the corners are not lifted up, we provide the torsion reinforcement at the corner. If there is no provision of torsion at the corners, then we need to refer to table 27 of IS 456. So now we have decided that torsion reinforcement is to be provided and it is simply supported on the beam of 230 mm width. So out of this table 26, which case has to be considered out of 1 to 9 cases? Out of these 9 cases, we need to consider one of the case. Since it is not been mentioned that whether it is an interior panel, one short edge continuous, whether the continuous edges are there, discontinuous edges are there and so on. So what they have mentioned, it is simply resting on the beam of width 230 mm. So what we'll consider? We'll consider case 9, that is 4 edges discontinuous. Since the edges are discontinuous, we will have only the positive moment at the midspan. Since the edges are discontinuous, we will have only the positive moment at the midspan. Since we have the positive moment at the midspan, we will have only one coefficient of alpha x and one coefficient for alpha y. And how to calculate alpha x coefficient? Depending upon the value of Ly by Lx ratio. So here we need to, next thing is, once we are done with the details given, we need to decide the depth of the slab. In order to find out that depth, again we are going to proceed with the span to effective depth ratio. And here in the span to effective depth ratio, for simply supported slabs, it is 35 and continuous slab it is 40 if mild steel is being used. But if HYST bars are used, that is high strength deformed bars are used, then we need to consider the values multiplied with 0.8. So approximately here we have considered the span to effective depth ratio as 30 and we have got the effective depth as 166. mm. And we have, based upon this calculation, we have assumed that overall depth is 180 mm and clear cover of 15 mm, so that we will be getting effective depth of 160 mm. Effective depth of 160 mm. So effective depth is 160 mm and overall depth is 180 mm. Then effective cover assumed is 20 mm. So you can assume 20 mm or 25 mm depending upon your design and the exposure conditions. So now the next thing is to find out the effective span. To find out the effective span in both the direction, whether it is in Ly direction or Lx direction. That is the center to center distance between the supports. So here the width of the supporting beam is 230 mm. So on either side 230 mm beam is there. So center to center distance means it turns out to be 6.73 meter, and in the Lx direction it is 5.23 meter. And the next thing, in the Ly direction it is 6.5 plus 0.16, that is the effective depth. The clear span plus effective depth value, it is 6.66 meter, and Lx value is 5.16 meter, that is clear span plus effective depth. So out of these two values of Ly, that is 6.73 and 6.66, we are supposed to consider the least value, and even out of the smallest value among the Lx, we need to consider this value, that is 5.16 meter. So now the effective value of Ly by Lx, they are being calculated. And now let's calculate the ratio of Ly by Lx, that is 1.3. That is 1.3. Now the alpha value is 1.3. So if the alpha value is 1.3, here alpha value is 1.3, so what we'll consider, for 4 edges discontinuous, the alpha x value is 0.079 and alpha y value is 0.056. So before proceeding with that alpha x and alpha y, let's calculate the loads on the slab, that is self weight of the slab and live load on the slab. Self weight is overall depth multiplied with unit weight of RCC, that is 4.5 kilonewton per meter square, and even live load or superimposed load is also 4.5 kilonewton per meter square. And even you might consider the floor load also, approximately 1 kilonewton per meter square, and if you consider that, the ultimate load will be on higher round, that is it will be 10 into 1.5, that is 15 kilonewton per meter square. But here they have not considered, the floor load, so it is only 13.5 kilonewton per meter square. Now, once we are done with the load on the slab, we need to find out the design bending moment and shear force value. Design bending moment and shear force. So, in order to calculate design bending moment and the shear force value, here we have the equation mx and my. Mx is equal to alpha x w into Lx square. My is equal to alpha y into w into Lx square. Here alpha x and alpha y values, they differ, but whether you calculate mx or my, the span to be considered is Lx only. You need to remember this point. Whether you calculate mx, moment in x direction, or moment in y direction, the span to be considered is Lx only. Span to be considered is Lx only. So let's calculate mx now. Alpha x value is 0.079 for 1.3 Ly by Lx ratio. 0.079 and alpha y value is 0.056. So we have only the positive moment for this case since the edges are discontinuous. If the edges are continuous, then we would have both positive moment as well as negative moment. Positive moment at the midspan, negative moment at the support section. So here the positive moment at the midspan of short span, mx is equal to 0.079 into 13.5 into 5.16, that is Lx value. Remember, whether you consider the moment in x direction or in y direction, you need to consider Lx only, that is 5.16. So with this, we get the mx value as 28.40 kilonewton meter. And the positive moment at the midspan of longer span, that is my. Now alpha y into 13.5 into 5.16 square. So my is equal to 20.13 kilonewton meter. So this is how we need to calculate my value. And now once mx and my they are being found out, the minimum depth required from the maximum bending moment consideration we need to calculate. So in order to calculate that, what we'll do, we'll assume mu is equal to mu limit. We assume mu is equal to mu limit, and the depth provided, or what we can write is mu is equal to 0.133 FCK square. This is for Fe 500. So depth provided is equal to mu divided by 0.133 FCK, that is 20 into B, that is 1000 mm. So it will turn out to be 103 mm, and this is depth required. So this depth required is less than depth provided. What we have provided is 160 mm. So if depth required is less than depth provided, then we can proceed with the further design. Or else there is one more method by which we can say that we can continue with the design, is the one which we have used in design of beams. That is mu is equal to this value only, and mu limit is equal to 0.133 FCK BD square, where D is the value to be taken as the value which we have provided. So if in that case, if mu is less than mu limit, then we can proceed with the design. So this is how we need to calculate the depth, whether it is safe to proceed or no, and the codal provisions, the coefficients alpha x and alpha y, and the loads. See here, if instead of 4 edges discontinuous, if it was given that there are 3 edges discontinuous and 1 long edge continuous, if it is being given that 3 edges are discontinuous, then we would get 2 alpha x values and 1 alpha y value. Why 2 alpha x values? Because we would get negative moment at the continuous edge as well as positive moment at the midspan. And alpha y value would be only the positive moment at the midspan. So we would have 3 moments in that case. And if we consider here one short edge continuous case, then we would have 2 alpha x values, 2 alpha y values. So there would be 4 bending moments, 2 positive bending moments and 2 negative bending moments. So in that case, we would get 4 bending moment values. So we need to consider, depending upon the case selected, we need to consider the moment calculation. So that's all for today. Please make note, depending upon the cases chosen or the case given in the numerical, we need to proceed with the alpha x and alpha y values and the calculation of bending moment. So in the next class, we'll proceed with the design of reinforcement the shear, check for shear, then deflection and detailing part. So that's all for today. Thank you. If you have any doubts, you may just ask. Are there any queries?